students. So I received a comment about doing exam-style questions for different topics of the syllabus or syllabuses. And so natural selection is a topic that is covered throughout different IGCSE and GCSE exam boards. So you can see some examples here. We've got the IGCSE Edexcel biology, you've got Cambridge, Oxford AQA biology, GCSE biology as well from the Wales GCSE. Then we also have AQA, OCR. So make sure that you check the specifications of your exam board to know what your learning outcomes should be. All right, so what will this video cover? So number one, we'll go over the basics of natural selection. So what is natural selection? And then we'll go over two real-life examples. So the peppered moth is one example. Another common example that you do need to know for some syllabi are antibiotic resistance in bacteria. And then afterwards, we'll cover some exam-style questions. So there's two that I've included here. One is an easier one, and the other would be a little bit more difficult. Okay, so let's go over what natural selection is. So when it comes to natural selection, we have individuals of the same species that show a wide range of variation. So what that means is, let's say rabbits, right? We have rabbits of different fur color, or we have people of different heights, for example. Or you could have butterflies with different patterns on their wings. So all of this variation is due to random mutation. So mutations are basically random changes in the DNA sequence, and that can lead to new alleles. So then these alleles different alleles would cause different variation. Okay, the second point is individuals that are more suited for their environment are more likely to survive and will pass on their alleles to their offspring. So an example of this is, let's say, if you have an animal that has a fur color that helps them to adapt better to their environment, helps them camouflage to their environment, they're able to hide better from predators, and that's why they're more likely to survive. And the opposite is true. Individuals that are less likely to survive, let's say, for example, they die before they are unable to reproduce, they can't pass their alleles to the next generation. Okay, and the third point of natural selection is over time, more and more individuals will have that allele and therefore will have that advantageous trait. Okay, let's move on to the next slide. So we're going to go over two examples. First of them is a pepper moth, and the next example will be the antibiotic resistance. All right, so once upon a time, you had two variants of the peppered moth. We have the lighter variant and the darker variant. So you can see here, you had these trees that were covered in lichen, and that causes these trees to have a certain texture and color. And you can see that the lighter variant of the peppered moth would have a better time camouflaging. You can see this here, and then you can't really see the lighter version in this picture. Now, what happened during the Industrial Revolution is that the air was covered in, or there was a lot of soot in the air, and that caused the bark of the trees to get darker. And now you can see which one had a better time camouflaging. That would be the darker version. So what happened over time is that the darker version had a better time camouflaging, which made them more likely to survive and reproduce because they were able to hide from their predators. And so over time, you would have more and more of the darker peppered moth. Let's do another example of natural selection in action. We have antibiotic resistance in bacteria. So bacteria, they would evolve pretty quickly because they mutate and reproduce at a faster rate. And it's a random mutation that causes the bacteria to become resistant to these antibiotics. And antibiotics are just drugs that kill or reduce the growth rate of bacteria. So let's move over to the next slide. So number one, a random mutation arises which causes the bacteria to become resistant to the antibiotic. So you can see in this diagram, we have normal bacteria that's in blue, and then you have this orange bacteria that developed a mutation that caused them to become resistant. And then what happens is that when they become exposed to the antibiotic, most of the normal bacteria, they would die, which would leave maybe some of the normal bacteria to survive, and you would have the antibiotic resistant one, which is the orange one, that would survive. So as you can see here, bacteria with mutation, they would survive, and bacteria without mutation, they're more likely to die. And then what happened is that, well, now they have more space to grow and multiply, right? And when they multiply, they pass on their alleles to their offspring, so that eventually over time, there are more and more bacteria that are resistant to the antibiotic. So this is a past paper question from the IGCSE biology syllabus. This is from the Edexcel exam board. So we'll be covering two questions, one from this and another one from the Welsh exam board as well, the GCSE bio one. Okay, so let's start off with the first one. The table lists different places in the world arranged in order from the warmest to the coldest. It also shows the average mass of a mouse found in each area. Use your understanding of natural selection. So sometimes it'll give you a clue in the question as to how to approach the question to suggest why the mice in Antarctica have a biggest average mass. So we can see from the trend here, the colder the place is, the greater the mass. So a good thing to start off with is to mention the trend that we see. So let's write that down. From the table, it shows that the colder the climate, the greater the mass of the mouse. Okay, so why would that be the case? So I'm just going to write it down over here, draw it out here. So if you have a smaller animal, right, your surface area to volume ratio would actually be pretty high. So there's a lot of surface area for which heat can actually leave the body. Whereas if the animal is much larger, you would have a smaller surface area to volume ratio. So you're generating a lot of heat inside, but not much surface area to actually release all of that heat, right? And so therefore, if an animal is living in a colder place, it would actually benefit them if the heat loss is reduced. So let's write this down here. For a larger mouse, the surface area to volume ratio is smaller, and therefore less heat is lost. So now we got to link it back to natural selection because that's what this question is about. So you can say the variation in the mass of mice occurs due to mutations. The larger mice are more likely to survive and reproduce, and would therefore pass their alleles to their offspring. All right, let's go over the marking scheme. So 1 mark for noticing the trend, which is the colder the climate, the greater the mass of the mouse. Another mark is for less heat loss due to the surface area to volume ratio being smaller. Another point you can also add is the greater the mass, the greater the insulation that mouse would have. So if you have more insulation, you would have less heat loss. Another mark is mentioning that variation is due to the mutations that occur. So that's actually 2 marks, one for variation and another mark for mutation. And then the 2 other marks would be the larger mice are more likely to survive and reproduce, and then pass on their alleles to their offspring. So those are 1, 2, 3, 4, 5, 6, 7 marks. Okay, let's move on to the second question. Okay, so Varroa destructor is a parasite mite of honeybees. A colony of honeybees affected by a parasite becomes weakened and eventually dies out. The parasite mite originated in Asia, where it is the pest of an Asian honeybee, Apis cerana. It has spread across most continents, arriving in the UK in the early 1990s and affecting the native European honeybee. Okay, so in 2014 to 2015, there were 1,650 registered beekeepers in Wales who kept bee colonies, each of which is 1 beehive. The National Bee Unit recommends that honeybees should be treated with pesticides to try and reduce the number of parasitic mite in beehives. So I think that's something to note. So parasites reduce the number of parasitic mite in the beehives. In recent years, many beekeepers in northwest Wales have stopped treating their bees with pesticide. These beekeepers believe that there is no difference in colony losses between bees treated with pesticides and bees not treated with pesticide. So here we have a table. So the table shows the winter losses and the number of colonies that die out between 2010 to 2015 in northwest Wales. So let me just do a little bit of brief annotation here. So this one would be kind of read together because this one is about treated colonies. And then this one would be sort of read together because this is about non-treated colonies. And so, for example, if you had 71 colonies, then 44 of them would be treated and 27 of them would be non-treated. So if you do 27 plus 44, that would equal to 71. Right, so that's just a little bit about this table. So let's go on to the next part. What percentage of beekeepers in Wales took part in the survey in 2014 to 2015? So we need to look at 2014 to 2015, this part over here. So if we add those two values together, 17 plus 65, that would give us 82. So 17 plus 65 gives us 82. So that's how many beekeepers. And then if we can see here, there were, in 2014 to 2015, there were 1,650. So we need to divide the number that we just calculated with that number. So we will do some percentage. That would be 82 divided by 1650. And then of course times by 100 because it's a percentage. So let's do that. And then what we get is 4.97%. So 4.97. Oops. All right. Part C1. Use the information in the table to state one conclusion about the effect of the pesticide on winter losses of bees. So let's scroll up to the table. So if we compare this column together with this column, you can see that with the ones treated with the pesticides, you have a much greater percentage loss. So you can see 27 versus 11, 8 versus 7, 41 versus 32, And another conclusion you can also make is if you look at 2014 and 2015, you can see that the percentage losses are the same. So those are actually two conclusions that we can draw from this. Let's write at least one of them down. Okay, so one conclusion about the effect of pesticides on winter losses on bees. So, when pesticides are used, there was greater percentage loss in winter losses. Okay? Alright, so give two reasons why some beekeepers across the UK would argue that the strength of the evidence of the survey is weak. So if we want to talk about the validity or how reliable the survey is or the experiment is, we would always need to go back and comment about how the survey or the investigation was conducted. So for example, they only did this survey in northwest of Wales, right? And you can see that there, northwest of Wales. And then it wouldn't be fair to make that conclusion for the entire population of bees, right? Another thing you can also say is, well, we have 1,650 registered beekeepers, but here, these are the amount of people that were involved in the survey, right? So you have a small number of people that have registered, that are participating in this survey. Okay, so let's write that down here. So we could say this is it in northwest Wales. Bee population and other regions. Another reason is that only a small percentage of beekeepers participated in the survey. All right, and then finally the last part is more towards the natural selection part of this question. As you can see here, sometimes they won't just have a natural selection question on its own. They'll combine it with other topics as well. All right, so let's look at part D. Early attempts at control of the parasitic mite involved using the chemical pyrethroid. By the late 1990s, the parasitic mite developed resistance to the chemical, and the beekeepers were advised to use other chemicals to control the pest. Explain why, over time, the pyrethroid chemical became less effective at killing the parasitic mite. So this is similar to antibiotic resistance, but instead we're talking about the parasitic mite's resistance. So first we have to talk about where this resistance is coming from, and that is coming from mutation. So there is a mutation in a gene in that parasitic mite that caused it to become resistant to the pyrethroid. And then what happened is that those with the mutation, when they were exposed to the pyrethroid, they did not die. Instead, they would survive, or more likely to survive, and more likely to reproduce, and then pass on that allele or that mutation to their offspring. And that is referred to as natural selection. So let's write this out. A mutation in the gene of the parasitic mite caused it to, sorry, that's supposed to be become resistant to pyrethroid. The parasitic mite that had the mutation survived, reproduced, and pass on the allele to their offspring. This process is referred to as natural selection. So let's go over the marks. Number 1, we have a mutation, and the second mark would be allowed it to become resistant to the pyrethroid. That's the second mark. The third mark is the ones with the mutation survived. The fourth mark is reproduce and pass it on to the next generation or to their offspring. And then the fifth mark would be natural selection. All right, so those are the marks. So this is a new format that I'm trying out. So if you guys have any questions about this video or about any other topic, just leave it in the comment section below. Bye!